We are at the top of the hour, so good morning and welcome to the webinar today. Our webinar will be 30 minutes along with time at the end for Q&A. During the webinar, you can send your questions through the chat icon, which is located at the bottom of your screen, and we'll be happy to answer your questions during the Q&A portion. We will be issuing PDH certificates for those attending the live session today that have elected to receive them. A copy of the presentation will be sent post-webinar. All of our webinars are available on demand at bartlettwest.com. We will continue to add webinars and encourage you to check back often. Today, we're going to hear from Tyson Decker. For the past decade, Tyson has been involved in the design and the construction of several design, bid, build projects, including drinking water treatment facilities, a water treatment plant expansion, a pump station expansion, and a residual handling facility in Southwest North Dakota. Today, he's going to be discussing how a GIS-based map of meter data can be used to identify areas where water demand diversification varies from the hydraulic model demand. With that, I'm going to turn it over to you, Tyson, to take it away.
Okay, thank you, Rebecca. Can you hear me?
I sure can.
All right, perfect. All right, thank you, everybody, for joining us this morning. I will get started. Okay, first thing I'd like to do is talk about the objectives today of the presentation. The first is, what is demand diversification in water systems and why is it important? Would also like to talk about using system data to analyze your system against the model and compare it with the actual demand diversification that you're seeing. And then the third thing I'd like to go through is the application and advantage of using GIS-based meter data, or the process of pulling meter data over into a GIS application. Okay, to start here, I will be talking largely about rural water system designs. This is applicable to nearly all water systems in some form or fashion. But the concept of demand diversification is very critical in the rural water setting, particularly because because there isn't fire flow included in the design. And so to illustrate this, looking at the slide there, this is just a simple graph showing the components of a rural water system, i.e. an intake treatment plant, a storage reservoir, and residence is connected on a distribution system. And with this, one of the most critical, if not the most critical design elements of a system design is something called the instantaneous peak demand, which is the short-term peak flow required by the customers. And that is primarily located downstream of the storage reservoirs where the residences are located on the system. Everything prior to the storage tank is typically sized as a transmission main or a transmission pipeline and is relative to the instantaneous, or not instantaneous peak demand, but the daily peak demand. So what is demand diversification? This really correlates well with thinking about a house, thinking about your home. This graph shows the primary residential end uses of water, and whether it may be a toilet, a shower, a faucet, clothes washer, or laundry, and other functions. And the demand diversification concept is this. It's the concept that not every user is going to use water or their own peak flow at exactly the same time. And to help explain that with an example, think of a water system where you have maybe 20 customers on a distribution pipeline. And say the peak demand of those customers is 5 gallons a minute. Well, when we design and model these water systems, it is not 5 gallons a minute times 20 to give you a total instantaneous peak demand of 100. It's much lower than that. And that is due to the low probability that every one of those customers is going to be pulling peak flow at exactly the same time. And this leads to this next graph, which is our system demand curves. And these curves are based on something we call service units, or just simply the number of customers that are on or served by any distribution pipeline. And these curves can vary, as this graph shows. They can vary based on usage patterns, experience, density, climate regions, and to help illustrate that, a couple different things. Say you're in a rural water system largely comprised of urban sprawl areas. That type of setting is going to have a much different demand diversification than, say, a largely rural system that is comprised of farmsteads with outbuildings and ancillary needs. Another factor with developing these curves is cost, obviously, and density. So if you were to design a pipeline and you had largely dense urban sprawl areas, it would be more cost effective or easier to maybe give those residents a higher demand curve, as opposed to areas where they may be sparsely populated in largely rural areas. And in that case, you may only be feasible to bring them a certain amount of water, and so then you would have a lower curve in that type of system. Now, thinking about demand diversification in these systems, there are exceptions. And I think that's on my next slide. Yes, so some of the common demand diversification exceptions or exclusions to that concept would be domestic livestock, farming, spraying, automatic sprinklers for lawn watering, and commercial industrial applications. In these instances, what we typically do from a modeling standpoint is we try to pull these out unless they are built into the demand diversification curve themselves. Some of that can get incorporated into those curves, or compensated at least. But another way we also deal with this that's more typical, or actually follows the usage patterns better, is we consider these base flows and pull them out entirely or aside from the demand diversification analysis and the curves you saw on the previous slide. Okay, so that's kind of the demand diversification concept, and this is all leading up to a case study example that I'll talk about a little bit later. But the next part of the presentation I just want to cover briefly, again leading up, is your water usage data and how we can use that to do two functions. One, maybe we want to optimize your hydraulic model for your system, or maybe you have a specific problem in your system that we may need to look at and try to figure out a solution for it. And every system has data. Every system has system-wide data, whether it's SCADA data from your treatment plants. Figure out a peak monthly usage, a peak day usage. Again, you can go to service area by service area and look at, again, the peak month usage, the peak day usage. Maybe you can even get some instantaneous peak usage from those specific service areas. But that's all great data, and that's typically SCADA data from flow meters, pressure instruments, tank levels, things such as that. The other side of it is localized data from your customers. Everybody has billing information, and if typically you'll have at least monthly usage data. You may have smart meters and have instantaneous data available at the end user. And then you also have your GIS maps with geospatial or layout information of each user. And so with that, we'll get into the case study. Kind of explain, this was a problem that came to us, and kind of explain the totality of the issue. The picture a farmer who's living in a rural water area, and he's using his water for domestic and many farm-related needs. And throughout the spring and summer, there are times when he needs to spray his crops, which are typically done on timely days when the wind is low. And when this happens, he doesn't have the flow and or pressure that he may need or what he is used to. And so his explanation of the problem would be something like, I have good water when I don't need it, and when I need it, I don't have good pressure or flow. So we got this problem, and instantly, being engineers, we got a lot of questions. What was the peak month for that area? What was the peak day usage? Do we have the ability to obtain any instantaneous peak data to correlate to our demand diversification model? And then the last question is, where is the water going? Who's all using water? Is it just this farmer? Is this largely spread across the service area or multiple service areas? And so what we did, this specific service area is a bit unique in that it was served by an inline booster pump station. So there's no tank and no gravity. It's an on-demand booster station. We gathered SCADA data and meter data and wanted to compare that with the hydraulic model and the complaints or the issue at hand here, and try to figure out what the root cause of the problem is and recommend a solution. Okay, the first thing, this is using SCADA data, looking at this particular service area over the course of 2 months, June and July, and looking for peak days, because we didn't know, is this something that happens once a month, 3 times a year, 10 times a year, 30 times a year? And really what this told us is there was about a handful, 7 or 8 days, where the usage in this service area was exceeding what was in our model and what was designed. So this next slide then is looking again at SCADA data at this booster pump station and looking at one of these peak days. We did look at all the peak days, but I'm not going to go through them all. I just picked one here. And this one was interesting because this told us a few things. So I'll just walk you through the information as there's a lot going on here. The red line is the discharge pressure. The green line is the suction pressure for the booster station. The blue is the flow rate, and the yellow or orange, depending on how it's shown on your screen, is the pump speed. And once we saw this, we learned a few things. One thing we learned, if you look at the green line, you notice that it flatlines after about hour 8. And really what that told us was that the water supply to this booster pump station was also dropping. And in order to maintain minimum pressures, so those upstream customers had proper and adequate pressure, that this pump station was getting choked off, if you will, and didn't have the pressure it needed to keep up with the demands. And the red line on this is the discharge pressure, and normally we would like to see the discharge pressure stay static and the flow rate vary. And really what is happening is the booster pump station could not keep up in this area and meet the instantaneous peak demands. Okay, and so we had analyzed all the SCADA data, and we still haven't answered the question of where is all this water going, and is this going to all the customers? Maybe they're all pulling more water than what was designed, or is this located to a few or specific to a few? And so what we ended up doing is taking the system's billing or metering information and pulling it over into a GIS-based platform where we were then able to create what we call a heat map, or like to call a heat map. And the heat map is categorized based on colors, the red being more than 2 service units of water in a month, orange being 1 to 2 service units, and then the yellow and greens are less than 1 service unit. And using this, really what we started seeing is this service area had about 22 users that were using most of the water. And as we suspected, nearly all of these high consumption users were farmers. And so we started looking at, just to confirm that our spraying theory or presumption was correct, and that those peak days, when we go back a couple slides and look at the peak days through the first, or through June and July, those do correlate with the low wind days in those months. Okay, and so then this is a kind of a blow up, and I want to talk a lot about this slide now. So this let's start with the GIS platform, because this shows a number of things here. At the bottom, you will see the tabular data. We pulled in 6 months of data from February through July of 2020, and that process probably took us about 4 to 8 hours. There is a couple caveats to that. The one thing we did have in this case was the billing information had account IDs, and the GIS, ArcGIS Online in this case, also had the account ID identifier for each user. So most of our time was spent just looking for anomalies between the two of them and correcting those. And then as far as the integration of the metering data into the GIS platform, it went relatively quick after that point. So that was the first thing. The platform itself does allow you to filter data, go based on layer. So in this case, we're looking at June 2020 data. And I also have it filtered to only show the users that are using 1 service unit or more in this area. And then of course, all those users get tabulated at the bottom like GIS does, and you can export it out and create lists of customers. So back to the problem now. What we ended up seeing is we had 22 users in this service area, and this, what we're looking at now, is one of the worst areas. There was 8 customers, as you can see. I'll just kind of walk you through. I don't know if you can see my cursor, but the north to south red line, that's a 6-inch main. The green line going to the right is a 4-inch main, and then it's 3-inch. And what we ended up seeing happening in this area is all these customers, all 8 of them, were pulling water at the same time due to spraying. And that creates a scenario that acts a lot like an open pipe. Everybody opens their tap and takes the water they will get. The pressure, especially for the guys that are further off the main, is going to fluctuate greatly. And so we looked at this, talked, okay, can we add, maybe to solve this problem, go back to the booster pump station and increase the pump size, since the water supply upstream of that was being choked off, as I showed in the Usingcada slide. That really isn't feasible without having a parallel project along with it. In addition, we could convert this system to a gravity system, putting an elevated tank in. The problem is this is service pressures are about 90 psi, and it would be an elevated tank. It would be costly. So I think where we ended up, or I shouldn't say I know where we ended up, and our recommendation to the owner in this case was these 22 users in here. They ranged with monthly water usage from 30,000 gallons a month all the way up to probably 200,000 gallons a month. So our thought was, if we go back to each one of these customers and we put in flow restrictors to still get them that 30,000 to 200,000 gallons a month, but if we can spread that out so it's not all at the exact same time, then those users that are further off the main are going to see more reliable pressure and more consistent flow. I think I maybe blew through that a little quick, Rebecca, but I think we're ready to take some questions.
Okay, so at this point, we are going to open it up for Q&A. Please send your questions through the chat icon. And as we wait a couple of minutes for questions to come in, I do want to thank you again for sharing your time with us today. As a reminder, a recording will be available on our website. Thank you, Tyson, for sharing your expertise with us.